If you have ever watched a long freight train pass, you may have noticed something unusual. The locomotives are not always at the front. Sometimes another locomotive appears in the middle of the train. On other trains, one or more locomotives are positioned at the rear. Occasionally, locomotives can be found in all three places. At first, this arrangement seems unnecessary. If a train needs more power, why not simply place every locomotive at the front? That would appear to be the easiest solution, but on an extremely long freight train, adding more power at the front can create another problem. A train is not one solid vehicle, it is a long chain of rail cars connected by couplers. When locomotives pull from the front, that force must travel through the connections between the cars. The couplers near the front must transmit the force needed to move almost anything behind them. As the train becomes longer and heavier, those forces increase. Acceleration, steep grades, curves, and sudden movements can place especially high stress on the connections between cars. Adding more locomotives at the front gives the train more power, but it also concentrates more force in the same area. Instead, railroads can apply power from several points along the train. The locomotives placed in the middle or rear are known as distributed power units, or DPUs. They are controlled remotely by the engineer in the lead locomotive and provide propulsion or dynamic braking from different locations. Their purpose is not simply to add horsepower, it is to apply that power where it is most useful. A locomotive in the middle divides the train into shorter force sections. Under power, it can push the cars ahead of it while pulling the cars behind it. A locomotive at the rear applies power from the back, reducing how much force must pass through the couplers near the front. On the heaviest trains, locomotives may be placed at the front, middle, and rear so that the work is shared across several points. This also helps control slack action. What is slack action, you may ask? The connections between rail cars allow a small amount of movement. As the train accelerates or brakes, the train stretches and compresses. On a very long train, each section does not react at exactly the same moment. One section may be stretching while the other is compressing, especially on grades or on super long trains. If that movement becomes too severe, it can damage equipment or increase the risk of a derailment. Applying propulsion and braking from several locations gives the engineer more control over these forces. The remote locomotives receive radio commands from the lead locomotive. These commands control functions such as throttle position and dynamic braking. The engineer can also monitor the remote units and confirm that they are responding. The DPUs do not always perform exactly the same action as the lead locomotives. Depending on the system and operating conditions, different locomotive groups can be controlled separately. This becomes especially useful in mountainous territory. A long freight train can occupy several different slopes at once. The front may be already descending while the rear is still climbing, especially at summits. A middle or rear DPU can help move the rear section uphill without placing excessive pulling force near the front. As the train descends, locomotives positioned throughout the train can also provide dynamic braking from several locations. Dynamic braking uses the locomotive's traction motors to resist the train's movement. Distributing that braking effort helps prevent the train from bunching together or stretching too severely as the terrain changes. Distributed power can also improve air brake response on extremely long trains. A freight train's air brakes are controlled through a brake pipe running from the front to the back. When the engineer applies the brakes, a pressure change must travel through the train. The cars near the front may therefore begin braking before the cars farther back. On properly equipped trains, a remote locomotive can initiate the brake pipe pressure change closer to the middle or the rear. This reduces the delay between different parts of the train and limits severe slack action during braking. It does not make a massive freight train stop immediately, but it makes the braking process smoother and easier to control. The number and placement of DPUs depend on the train and the route. Railroads consider the train's weight, length, cargo distribution, terrain, and allowable in-train forces. A train crossing long mountain grades may require a different arrangement from one operating across relatively flat plains territory. More locomotives are not automatically better. They are expensive to operate, and every locomotive assigned to one train is unavailable for another. Railroads therefore try to use only the power needed to move the train safely and efficiently. Distributed power also creates challenges. The remote locomotives depend on radio communication with the lead units. If communication is interrupted, the engineer is alerted that the remote units are no longer responding to new commands. Depending on the system and railroad procedures, the engineer may need to change how the train is handled or stop until communication is restored. The locomotives must also be operated carefully. Too much pulling force at the front can overstretch the train, while too much pushing force from the rear can compress it and reduce stability, particularly on curves. DPUs do not eliminate forces acting on a freight train. They give the engineer more control over where those forces are applied. Without distributed power, railroads might need to shorten trains, reduce their weight, or use other operating methods to remain within safe limits. The locomotives in the middle and back are therefore not simply extra engines meant just for more horsepower. They are positioned there because on a long freight train, where the power is applied can matter just as much as how much power the train has in total.